How are you guys? Welcome back to my YouTube channel. We're still under engineering science and 4. We're still under stress and strain in young modulus. So I've given this typical question. Question 6, 6.1 says define young modulus. Defined the young modulus. And 6.2 says states the Hooke's law. Okay, first one says define the young modulus. That is our 6.5 define the young modulus. You want to know what is young modulus. Young modulus. Young modulus is a it's a mechanical property. All right, it's a mechanical property that measures is the one that measures the what we call tensile or what we call compressive stiffness of a solid material when a force is applied or applies, let me just say applies lengthwise, when applies lengthwise. So this is what we have. Young modulus elasticity, it's a mechanical property that measures the tensile or compressive stiffness of a solid material when a force is applied lengthwise. So this is what we can call that. So again, we're given to define this guy, which we call this guy, let me say we have them, call this guy Hooke's law. uh Hooke's law states that for an object, for an let me just say for an elastic object, for an elastic, let me just make it suitable, for an for an elastic object, the strain, we know that the strain is directly proportional, but the strain is directly proportional to the what we know, guys, to the stress causing it. Right, this is a young Hooke's law states that for an elastic object, the strain is directly proportional to the stress causing it. This is how we defined these things, guys. So far, this is how we define these things. So nevertheless, I can do this here, since FCFC can erase this. All right, must know that definition. So we're done with that. Let's check now our 6.3. We're given the 6.3. What does it goes on there? 6.3, we have given a compound. Check that is a compound shown in figure 3. Here it's our compound. Figure 3 below consists of cylindrical section. Here it's our cylindrical section, as you can see. Then I can call that, okay, it's part 1 or this part 2 is up to. Okay, you can call in, you can say this called part, you can call this part 1, object 1, then that one I can say just 2. Yes, you can see that it's a square. They say there's a cross section with a height of 50 millimeter, then the radius is 40. Talking about the radius, not the diameter. Okay, we have the radius there. If we want the diameter, if we have given the radius, that means the diameter is what, guys? From there till there, the diameter will be 8. So the diameter will simply equals to 80 millimeter. Then the Young modulus we've given, there is 110 gigapascal, and the tube side, this is a tube, is 15 millimeter. Okay, that side is 15 millimeter. The tube side there is 15 millimeter. Ish. The Young modulus of this, it has 210 Young modulus of elasticity of 210 gigapascal. Says calculate the final length of the compound, all of the compound, when the tensile, we've given the tensile is applied as shown in the figure below. You see, as shown here, you see is pulling up there. We're elongating this, is pulling there. So you can see it's pulling. This is a tensile. We're pulling, we're stretching this of this compound. All right, by the way, let's see how can we attack this. Says we should calculate what, the final length. All right, we know that the final length, guys, final length, let me just say, we know that the final length is equal to initial length plus the change in length, which is x, or you can say like this if you want. You can say, which x is simply extension, or you can say the change in length like this. So the aim is to get the change in length. So let us strive to find the change in length. So how can I find the change in length? We know, guys, the change in length, or you can say x, you know that x, remember x and change in length, it's a one and the same thing. So it's up to you which one you use. You can say change in length, or you can use x. This is a one and the same thing. It's up to you which one do you prefer. So okay, let me just say change in length is equal to force multiplied by the original length divided by area multiplied by Young modulus. But now we have two objects. Why don't you say there's change in length for object 1, change in length for that, change in length for area 1, Young modulus 1, the force is the same. Remember this, it's I can say object 1, which is the Q cylindrical, plus F2 change in length, multiply for the second object, the area of the second object, multiply, let me not say, multiply by the Young modulus of what, of the second object. The first object, I will choose the first object. Our first object, I will take the first object to be equals to the cylindrical. The second object, I will take that to become what, the cube there. So let me not put 1 here, simply just the change in length. This is a total change in length actual for the whole compound. Is a change in length for the whole compound. So since we did this, guys, we have our change in length. What is the force? Remember, the force is the same, is 350. If told that it's 350, is acting on the whole compound, So as you can see, it's acting on the whole compound, but we have 350. So kilonewton, yeah, we have 350 kilonewtons times 10 to the power of 3 multiplied by the length of object, what, 1. The length we're given of the silical, they've told us that the length of the silical section, the height is 50. We can take that as a height 50 millimeter. It's the same as what is 0.05 divided by the area. The area, guys, area, we've given the radius. They were focusing the shin. Where is the we've given the radius? The diameter will be same as 8, because we've given the radius, the diameter will be 80. Then 80 is the same as 0.08 when you divide by 1000. So the diameter is same as pi over 4 multiplied by 0.08. We square this. So multiplied by Young modulus of this guy. What is the Young modulus of the second portion is 110. Then multiplied by 110 times 10 to the power of what, of 9. It's for the first portion. So let us check for the second portion now. Force still the same, is 350 times 10 to the power of what, of 3. The length of 2 of the cube. What is the length? We've given that the sides will simply, what, 15 is the same throughout, we know it's 15 millimeter. Then we know that 15 is 15 millimeter, that one. So this is the same as 0.015, isn't it? Divide this by the area. Remember, the area is simply of the square is the area of the square is simply equals to 0.15. You multiply again by this, is simply just square this. We know most the area of the square is like that, isn't it, of the cube, length squared. So alright, multiply by Young modulus of the square second portion. Young modulus there of the second portion, they said is 210 there. As you can see, 210 there. So 210 gigapascal, 210 times 10 to the power of what, of 9. So we can punch all of this. Let's try to punch all of this into our calculator and see what is the value that we'll have. Remember this change in length of this compound. It's okay. We have there 350 times 10 to the power of 3. All right, 0.05. All right, we're checking here our things. All right, multiply by 110 times 10 to the power of 9, which is, this is our Young modulus. All right, plus now 350 times 10 to the power of 3 times 0.015, divide this. Okay, 0.015 squared times 210 times 10 to the power of positive 9, like this. All right, this is what you're supposed to have. Let me check. I think on the calculator this thing is the space. It's a matter of the, I think this takes up the whole space. Alright, let me punch this same time and check. Alright, what I will get. Okay guys, I think now it's fine. I've double checked here, sorry about that time. Alright, this will be equals to what? 111,111 times 10 to the power of minus 6. This is in mid. That is our changing length. Now we want the final length. Remember, the aim is to get, we know that the final length is what is equals to the initial length plus the changing length. That was the aim. So the initial length will be of the, again you must be wise, the initial length will remember it's a compound, will be from there until from there going there. You add up this initial of this and add up that. So the initial length, guys, will simply equals to what? The initial length will be the sum of what? Will be, we had 50 millimeter, or yeah, we had 50, or it was what, the 50 millimeter plus 15, just our initial, this one, remember, without plus now the extension. This is our extension now, it's in mid. So let us make our extension to become in what, let's multiply by 1000 so that this will be in millimeter. For this to become in millimeter, this does not change anything almost there. Okay, it does change. So 11.11 times 10 to the power of minus 6 times 1000. This will be plus 111.111 times 10 to the power of minus 3. Alright, so we're adding now. We'll have the final length. This is our final length of the compound. If I'm adding all of these, simply have our final length. So 50 plus 15 plus 111.111 times 10 to the power of minus 3. This will be 65,111 millimeter. So this is how you find, this is how you go about dealing with that. So what do we have again? We have this typical question. So we're still under the same question now. We're at 6.3 now. We'll deal with 6.4. 6.4 says inlet leaves and pin hook in figure 4 shown maximum force of 90. We have maximum force of 90 kilonewton and applied if a maximum shear strength is a shear. They wanted to precise shear stress, okay, of 60 megapascal is allowed in the pin. Says calculate the diameter of a suitable pin. Remember, check, I've said, guys, if you are given something like this, if you see something like this, I said here we'll have a double shear, guys, double. It will shear there. We'll have a double shear there. Yeah, alright, we'll have double shear. Always, I've spoken about this. You have given this thing of the hook. Given the hook, guys, will have a double shear there. So you multiply your area by what? By 2. Do not forget to do that. So we're supposed to calculate what here to determine the diameter as far as possible. So all right, you can see 6.4. We want to calculate the diameter given the force and the shear stress. Okay, by the way, shear stress is equals to force divided by the area. Now we'll multiply. Remember, the area will double the area. We'll double the area. We'll have a force multiplied by 2a. We want to make a. Okay, we have this. But we want the diameter. We know the diameter. We'll get it from the area. We can try to make area the subject. You multiply there. You'll have 2a multiplied by shear stress equal to force. You divide by these two. You'll have that area will be what? Force divided by what is that? 2 multiplied by shear stress. So this is what we want. We want to calculate the area. Why? Because I've told you guys the diameter is equals to, when you multiply, will be 4 multiplied by what? By the area. 4 multiplied by the area divided by what? By 4. This is what we're supposed. The aim is to get a there, which is the area. I've shown you when you do your manipulation. This is pi, isn't it? From our manipulation, guys, we know that area is equals to pi over 4 d squared. Then you multiply by 4, then I divide by pi, will be a multiplied by 4 divided by pi. Then I'll left with d squared. Take the square root both sides, so d will be equals to what? To that a multiplied by 4 over, as you can see, it's a method of manipulation. So okay, let us substitute, guys. Area, the force there, they've said the force is what? Is 90 kilonewton. We have the force to be 90 there. 90. This one was 60 megapascal. So we have 90 and 60. So 90 times 10 power 6 multiplied by 2. Then the shear stress is 60 times 10 power 6, or this is power 3. This is kilonewton. This is like that. So this is what we have. Then what will be our area? 90 multiplied by 10 to the power of 3 divided by 60 times 10 to the power of 6. Area will be 75 times 10 to the power of minus 6 meter squared. That is our area. Then we know they wanted the diameter. The diameter, as we have seen, is equals to 4 multiplied by area divided by pi. So this is what we know so far. So nevertheless, let us sharp our thing for the area divided by pi. So therefore, what will be the diameter? So square root over 4 times 750 times 10 to the minus 6 divided by pi. All right, our diameter there will simply equals to 30,902 meter millimeter. Remember, you'll have this. I just write that to pin meet. Remember, on your calculator, we'll have 30,90. Okay, 902 times 10 to the power of minus 3 meter. But obviously, to become in millimeter, multiply by 1000, so that will be in millimeter. This will be 30,902 millimeter. So this is what we have so far. That is our diameter. We're done. Let's check now. 6.5 says a round bar with a diameter of 15 millimeter and a length of 1.2 is subjected to a load of 150. If noted that the change in length is 0.325, calculate the 6.5.1, calculate the stress in the material. All right. Calculate the stress in the material. All right, guys, we know that the stress is equals to force over area, isn't it? So another thing, guys, stress again is measured. If they give you stress with SI units like this, Newton per meter squared, this is simply a stress. Don't panic. Remember, the force is measured in Newton, then the area is measured in what? In meter squared. If they give you something like this, do not panic. It's still what? The stress, or which is a pressure. It can be a stress also, or it can be a pressure. Do not panic if they give you something like this, Newton millimeter squared. Do not panic. Just convert this, guys. They can give you, they can be tricked. They can say Newton per, but they can give you stress that it's in millimeter squared. If they give you again like this, do not panic. Millimeter squared, to convert millimeter squared to a meter, you multiply this by times 10. Just know that you multiply this by 10 to the power of minus what? 6. Multiply this to the power of minus 6. This will be what? Meter squared. You must know that. So to be meter squared, you multiply by this. So I'm just highlighting things that you're supposed to know if the question can appear like that. But nevertheless, we're here. We have 150 kilonewtons divided by the area I've given. Obviously, diameter is 15. All right, diameter is 15 there. Can say this will same as 0,015 square. All right, then we'll have the stress in the material. What will be the stress? Simply punch this, then we'll have the stress. 150 times 10 to the power of 3 divided by pi over 4 into 0,015 squared. This will be 848,826 megapascal. Right then, what do we have? 6.5.26. Calculate the strain in the material, guys. The strain is equals to change in length over original length. Also, the strain, can get the strain if you have given Young modulus. You know that Young modulus is equals to what? To stress over strain, and make strain the subject. If you make strain the subject, it will be stress over Young modulus. You can get it like this. Again, let us check what do you have. You are not given Young modulus. So since you are not given Young modulus, the one of young modulus, it won't work. We don't have young modulus here, so this one it's out. This one it's out because we don't have young modulus. Let me erase a little bit here the bottom. All right, so we are forced to calculate this. We're forced to find that strain. So we have the original, the length of 0.1. You noted the change in length we've given. You see there we've given this is nice. The change in length here, it is 0. We've given to be 0.32 millimeter. Okay, that is it. So 0.32 millimeter to become in meter. Multiply this by power minus 3. This will be what will be in meter. Divide by the original length, which is 0.2 meter. 0.2 meter there. Then this is what it's 0.2. Oh, it's 1.2. Why am I keeping saying 0.2? It's 1.2 meter. There we have 1.2 meter. So meters and meters will cancel, as you can see. So we have no SI units. This does not have SI units, guys. It won't have SI units, as you can see. Then our strain will be what? 0.32 times 10 to the power of minus 3 divided by 1.2. all right, it has no SI units. 226.667 times 10 to the power of minus 3. This is our strain. All right, so guys, this is what we have in this typical video. So thank you for watching. Thank you for watching. And then please note, if you have not subscribed to my YouTube channel, may you kindly subscribe to my YouTube channel and click the notification button so that you'll be notified whenever I post a new video. Feel free to comment and feel free to share this to your fellow classmates. All the best. See you on the next coming session.